Good morning, everyone.
Hey.
Hope we had a nice weekend. We have my dean here today observing as part of my normal tradition of re-upping our contracts and stuff of that sort. So Dean Abakbe is here. Everybody say hi to Dr. Abakbe.
Hey, everyone. Hello. How are you all? Don't pay attention to me. Just concentrate on your instructor and understanding the subject. That's all.
Thank you, Dr. Abakbe. He's a physicist too. He used to teach an astronomy class that he let me have some time ago. So this ought to be fun. We're of course still working in chapter 29. I've now finished everybody's midterm. Basically, everybody's now had many opportunities, of course, to complete the midterm on time. So I was telling you guys that I know the midterm grades were not that high, and I had warned you that that would be the case. But I want to let you know what my plan is always every semester is that first midterm is the only test you take, or the first test you take, in which you're actually proctored. You're not allowed to search the internet. You are allowed, of course, your equation sheets, but you just can't do. Told you if oh yeah, I understand. Sorry, I just caught Jasmine talking to me. So yeah, no problem. So what I wanted to tell you guys is my plan is, as always, is if you end up doing better, on the final than you do on the midterm, then I'll substitute your final exam grade for your midterm grade. I don't do the other way. The final is really the big show, if you will. That's where you got to peak. So that's how that's going to work. So there's not going to be any kind of curving or anything on the midterm. It's just going to be, hey, this was a learning experience where you realized, perhaps some people realized they were leaning too much on the extra resources that were available on the regular online test, where I tell you, you can use the internet, you can use your notes, you can use your book, you can use Google, all that good stuff. So that's my regular online test. But by you doing those in the practice test, you get a lot of homework experience, which is really the main reason why I do this whole system. And then the midterm comes up, and that's usually where everybody discovers, oh crap, I didn't realize how much I was leaning on the ability to do searches during tests, even though, you know, I limit the time. So hopefully everybody's now learned a little bit, and you'll be able to do much better. And that generally is the case for the course. Generally, students do a little better, usually on the order of a letter grade or two higher on the final than they do on the midterm. And automatically, if your final exam grade's higher than your midterm, I just automatically substitute that in. You don't have to ask me to do it or anything like that. I do that for everybody. So make sure you learn how to study a little bit better and how to take tests with less resources. In other words, you've got to have enough experience solving problems that when you face a problem on a test, you only maybe need to look up 1 out of 20 questions. And that's just because you forgot some, you know, minor point or something like that. So anyways, didn't want to spend a whole lot of time doing this, but I just want to let you guys know that, yeah, Mr. Younger's got your back. If you didn't do so well on the midterm, I completely understand. If you did well, which we actually had some people got 95, 98, that sort of thing. If you did well, that's great. And I'm not gonna trade your midterm grade for your final. So just make sure you just do equally well in your final, and your grade will be fine. Of course, these are the only 2 tests that you have where I literally can say 100% certain that the person that is getting the grade is the person taking the test. So that's why I weight those 2 so heavily, but that's also why I don't wish to harm you on the midterm. Okay, so don't stress too bad if you didn't do well. It's not uncommon to have even in the low 50s for that midterm. So if you're even slightly lower than that, don't worry about it. I would personally let you know if I thought you needed to drop, and I haven't really seen anybody that needed to drop except for some people that have missed several tests. So anybody have any questions on course material or anything else before we move on?
I have a question.
Yes, go for it, Krisha.
Were all of the homeworks that were scheduled for mastering physics last night supposed to be due?
Yes, that's why I've been warning everybody about. You had some past chapters that were due. Now we've only covered up through chapter 29. We're only in 29 now, in fact. So anything after 29 are back in this the chapters on thermodynamics, which are like 17, 18, stuff like that. Those haven't been covered, so those dates are irrelevant. That's just where mastering throws them in there at random days almost. So the only thing that should have been due is somewhere between 21 and 29. And I think 29 is not due until this Sunday.
So basically just ignore the teens, like we'll see them up there, but they don't need to be done.
No, nothing's going to be done. We started on 21 and we're at 29. Only those dates are relevant. If you see any more, don't worry about it. They're going to change later. We are actually going to go back and cover some thermo. This is a weird way we do it here at TCC. We cover basically kinematics and dynamics and relativity in the first semester, and then we go back and hit harmonic motion. And if we have time, we actually go into elementary particles. Then in the second semester, we do electricity and magnetism, jump back and hit thermodynamics, and then we go forward and do quantum mechanics. And if we have time, nuclear physics. So that's just the way this course is set up, because we can't offer, well, we could offer, but we've seen that when you offer a 3-semester sequence in physics, which is what most universities would do, we can't get a third semester to make, just because not enough students want to be around an extra third semester. Most people will come in and can't take calculus-based physics at least till their second year. So, anything else?
Yeah, actually, I got a question, Professor.
Go for it, Brett.
I think I might have missed or just didn't realize, but were chapter 17 homework conceptual, chapter 18 and chapter 19 all due on the same day?
No, we haven't covered those. Like I told people before, our standing rule is any chapter we haven't covered, the dates are relevant. It's just a matter of sort of when I build the course, I have a couple of ways I can set it up. And the most efficient way, at least for me, is to just let it choose things. Well, this time it chose some really weird chapters. So you're only responsible for 21 through 29 so far.
Okay, I just got worried logging into mastering physics and seeing like 4 things not like, you know, done.
Yeah, I
like,
forgot those were out there. I went and changed the chapters 30, 31, and the quantum mechanics ones, but I forgot about the thermodynamics ones. So that's why they're not changed back yet.
Got it. Okay.
No fret. All right. So we were on chapter 29, which is electromagnetic induction and Faraday's law. And with that, we can actually do some pretty neat things. I've already shown you a few things. I showed you about moving a box through a uniform magnetic field. I'm going to do some stuff like that. And in fact, the first problem I'm going to do is kind of wordy, and I didn't want to waste my lecture time in actually writing it in real time and drawing it in real time. So I went ahead and wrote it out beforehand, and then we're going to solve it. So hopefully you'll be able to see it. I'm going to turn on my document cam, make sure no one has any more questions before I go. Okay, looks like we're good to go. All right, so here's my document cam. Make sure it's in focus. It says a 1,000 loop square coil of wire whose sides are L equal 10.0 centimeters. I'm basically trying to make sure everything has at least 3 sig figs here. So that's why you see like these little dots there and stuff. So it's a 1,000 loop square coil of wire whose sides are L equal 10.0 centimeters long and whose total resistance is 300 ohms. Is pulled through a uniform magnetic field pointing out of the page as shown. So there's the rectangle, or actually the square of wire, and it's actually 1,000 turns around there, and it's being pulled. You can see that little green arrow pointing to the right. It's being pulled to the right, and those arrows, the circles with a dot in the middle, represent the front of an arrow, like you shoot from a bow and arrow. That means the magnetic field is pointing out of the page. Okay. The magnetic field is actually a big one. It's 1 Tesla. Remember, the Earth's magnetic field is about half a Gauss. So that's like 10 to the -4th Tesla. So this is a big one. This is not quite as big as your MRI would be necessarily. I think most MRIs are on the order of 1.5 to 2, and they even have some up at 4, if I'm not mistaken. So anyways, the magnetic field is a 1 Tesla field, and when the right edge of the loop encounters the right edge of the magnetic field area, it takes 0.100 seconds for the coil to be completely removed. So basically, we start the timer when this edge right here gets lined up with this edge right here, because this is where the magnetic field abruptly falls to an end. So we pull it, pull it, pull it, and then it gets right about here. And then we start the timer, and lo and behold, you pull it out in 0.100 seconds. So 1/10 of a second. I want to know, A, what is the flux initially? And then we're talking magnetic flux, of course. B, what is the rate of change of the flux? C, what is the induced EMF? Remember, EMF is electromotive force. D, what is the induced current? When you have a resistance, you can actually find the current. And E, how much energy is dissipated in the coil? And then finally, F, what is the average force required to remove the coil? Okay, so that's the first problem we're solving. It's like I said, it's a lot of words, but the main thing is I wanted to write it down, have it written down for you, read it out loud on the video, and then when we get to when you go to look at your video on the YouTube channel, you'll be able to see everything again. Okay, so let's go about solving it. I'm going to write down the things I know, and then I'm going to write down how I'm going to solve it. So what I figured out so far is that the magnetic field B is equal to 1.00 Tesla. Okay, I know that the length of the square is 0.100 meters. In other words, it's 10 centimeters. Okay, I know that the N, the number of turns, is equal to 1,000. And I know the time, delta T, it takes to pull it completely out once it gets to the edge is 0.100 seconds. And finally, I know the resistance R is equal to 300. I'll put a 0.0 and underline it. Reminding you that that underline means that's not a sig fig. Okay, and ohms. That way I don't have to write that stupid decimal all by itself. Okay, so first off, what we want to do is find the flux initially. So A, we're going to use our definition of magnetic flux, which is the magnetic flux is equal to the integral of B dot dA. In this case, we're lucky in that we just have a uniform magnetic field that's represented by the fact that I told you it's uniform, plus I tried to draw the circles at equally spaced intervals, and so on and so forth. So that B is not going to change. So that ends up basically being a constant that you can pull out in front, and then you just get integral of dA, which is just the area. So I think you can all see that would be B times L squared. Does that make sense? Now I'm going to be working this algebraically like this, but I'm also going to compute the numbers, because at the end you'll see that not only are two answers the same, but they're exactly the same. So that's why I'm doing this, something I don't normally do. So when I put this in, I'm going to get 1.00 Tesla times 0.100 meters squared. A Tesla meter squared is the unit of flux, but they actually call that a Weber, W, capital W, lowercase b. And you can see this is 1/10 times 1/10, so that's 1/100th times 1. So that'd be 0.0100, and that's the Weber. Okay, so that's the unit, the Weber. Easy peasy, right? Now B, they're asking for what is the rate of change of flux. So what they want to know is d phi B over dt. Okay, well, when we look at that, we can see that it's actually going to be a little different, because d phi B over dt is going to be approximately equal to the average change in flux divided by time. So when this rod, the right edge of the rod part is here, lined up with the right edge of the magnetic field, I'm going to have the flux equal to BA, or 0.0100 Webers. And then in 0.1 second, I'm going to yank it so fast that it has a flux of 0. So the change in flux is final minus initial is actually equal to 0 minus, now we found the flux was BL squared, so I'll write that there, over delta T. So the answer is actually negative BL squared over delta T. And of course, calculating that 0.0100 Webers divided by 0.100 seconds. Now, a tenth of a second dividing by that is the same as multiplying by 10. So we're back to 0.100, and that's Webers per second, which happens to be a volt, by the way. Okay. So that's the change in flux, and it's technically negative, but we're actually not going to worry too much about that sign in most of this because we're really just thinking more about the magnitudes. So that was part B. What we want to know now in part C is what is the EMF? Well, that's Faraday's law. Faraday's law says E is equal to negative. If you have a number of turns, it's times N d phi B over dt. So that's Faraday's law. Does anybody have any questions on that? Anything so far? Looks pretty straightforward, right? Okay, just making sure. All right, so now I've got this negative, and now you can see why I really ain't going to care anyways, because the negative is going to work itself out. So the induced EMF is going to be negative 1,000 for the 1,000 turns times approximately. So I'll put a little approximately there because we're using an average change in flux as opposed to an instantaneous rate of change of flux. So that'll be times negative 0.100 Webers per second. And you can see when you multiply 1,000 times 0.1, you're obviously going to get 100, and negative cancel out. So I'm going to get, in fact, 100.0 volts. Again, the Weber per second is a volt. Now you might notice, remember, d phi b over dt is negative BL squared over delta t. So this is also N BL squared over delta t. So that's the algebraic form of that answer, just so we can keep track of that. Okay. So again, I'm trying to keep track of the algebra because at the end we're going to get a expression symbolically with symbols, and I want you to see that it's exactly the same. So it's just one of those neat things in physics. Now we're up to part C, or excuse me, to part D. And part D, it says, what is the induced current? Well, that's actually easy. We know that Ohm's law says V is equal to IR. In this case, the V is our EMF. So we can say that I is equal to the EMF over R. Well, we know that's N BL squared over R delta T. So that's completely how you're calculating it, but we're just going to take the numbers and make it nice and easy. So that's 100.0. Again, that's not a sig fig. It's just letting us know that there's 3 sig figs. And I'm just going to divide that by R. And the R is, of course, 300 ohms. Again, that's 3 sig figs as well. So 100 divided by 300 is basically 1/3, which is 0.3333. There's that extra sig fig thing. And of course, this is amps. So it's about 333 milliamps is the current that we have. Any questions on that part? Okay, so now we're going to jump to part E. Try to give us a little bit more room. So part E is asking for how much energy is dissipated in the coil. Well, the energy dissipated in the coil, you might recall, power is equal to IV, but there's other forms you can plug in. If you, for instance, you want to get rid of V, you can plug in IR for V, and then P equals IV becomes P equals I squared R. That's the one I'm going to choose. Okay. So looking back at what I was, we see I is this thing. So now I'm going to say N squared B squared L to the 4th over R squared delta T squared, and then times R, which obviously gets rid of one of these R's. So I have N squared B squared L to the 4th over R delta T squared. Now that's not how I'm going to calculate it. I'm just going to take my current, square it, and multiply it by R like I did before. But again, I have this algebraic version that allows me to apply this to any situation like this, not just the case where L equals 10 centimeters. So that's the other side of why we're doing it. Like I normally solve a lot of problems just with the algebra. All right, so we're going to take the I squared, which is 0.3333 amps. I'm going to square that and multiply it by 300. I'll put that extra sig fig there, and that's ohms. So this is actually going to give me the power in watts. And if I multiply 1/3 by 300, I think you all can see what that is. P equals I squared R. Okay. Excuse me. I said 300 times 1/3. It's actually 300 times 1/3 squared. So it's really 3.333 joules, or excuse me, watts. So the power dissipated is 3.33. I want to double check my math there because obviously I stammered a bit. So 0.333 times 300. And I get, oh, yeah, that's what it was. I thought I was coming off a decimal place wrong. 0.333 squared. Oh, excuse me. I know what's going on. I did ask for the power. So yeah, this is good. So the power is going to be I squared R. And what did I ask for? Oh, I asked how much energy was dissipated. That's why I'm getting off. Okay. So the power is going to be 33.33 joules, right? But what we want to know is the energy dissipated. Well, energy, which is sort of like work, and power, remember, is dW over dt. So with that in mind, you can say, oh, well, the work, which we're calling the energy dissipated, is actually just power times delta T. So that's the actual power, and that should have came out, I said joules, that should have come out in watts. Sorry about that. Any questions on that? Again, this is just sort of a sideshow so we can keep track of things, but this was the actual version that I used. I just took I squared R, multiplied 0.333333 squared times 300. That gave me 33.33 watts. Now, E, the energy dissipated, would be P times delta T. And that, of course, is 3.33 watts. Remember, that was one extra sig fig times 0.100 seconds. And that's going to give us 3.333 extra digit joules. Okay. Believe it or not, there's a reason we're doing this. So they're asking you to calculate the energy dissipated. And recalling that power is usually defined as dW over dt or even dE over dt, that was, I used the dW on purpose. The reason why is because part F, it says it wants to know what the average force is. So if you think this is the power dissipated, then where did that power go? It didn't just disappear. Obviously, it was supposed to go out as I squared R power, which would be heat. But could that really go out in 0.10 seconds, 0.10 seconds? I don't think so. So in fact, that power must have been applied basically or absorbed by sort of the work being done. So if you think in terms of work now, you can say, wait a second, for part F, they want to know what is the average force. And we know work equals the integral of F dot dL. That's our normal scenario. Well, I could say work is approximately equal to F average times X, whatever distance it traveled, right? That would give me that the average force would be the work done divided by the distance traveled. Well, the work done is this 3.333 joules divided by the distance of, remember our L was 0.100 meters, or 10 centimeters, in other words. So this is the same thing as multiplying by 10, and lo and behold, we get 33.33 newtons with one extra sig figs. So that's the average force. Now, this is interesting. That force doesn't mean that much, but check this out. If we actually used our traditional equation for finding the force due to a magnetic field, we had dF is equal to I dL cross B. Remember that one? Well, in this case, we got a uniform magnetic field we're assuming an average force, but we got a uniform magnetic field. A current obviously is going to be somewhat uniform times DL. If I actually tried to do that, this would become B times I times L. And when you actually calculate B times I times L, you have to, of course, realize it's not just one I, it's N I's. So because there's N currents running by, right? So I'm going to make it BIL and then N times as many forces. So when I actually calculate it this way, I'm going to get 1.00 Tesla times the current, which we found was 0.3333 extra unit there, amps, times 0.100 meters, that's the L, and then times 1,000 for the number of turns. Now, what you can see here is the 1 is not going to change the number. The 1,000 is going to make this 333.3, and this is going to make it 1 decimal place smaller than that, which in fact becomes 33.33 newtons. And remember, that's a Newton, not the N from from the other thing. So in fact, our regular electricity and magnetism equation gave us the same thing as our work equation did. And the reason I was carrying all these things along, again, not just so you have a symbolic answer that's true for all problems, but at this point we can figure out that P obviously is N squared B squared L to the 4th over R delta T. If I multiply that by delta T, that'll give me E. And then if I take that E and divide it by L, I'll end up getting, I'll write it right up here. So notice I'm taking the power, which is N squared B squared, and now I'm taking L squared, or L to the 4th, excuse me, R delta T squared, and I'm multiplying it by delta T. So that's going to get rid of one of those. Let me get a marker to mark that out. So this delta T squared is going to move that, and I'll just have 1 delta T at the bottom. And then I'm going to divide that by L. So lo and behold, this force is actually equal to N squared B squared L cubed over R delta T. Well, if you actually put in B, which we know, L, which we know, N, which we know, if we put in the I, we will actually get exactly the same formula, because you can tell here, I, when we did it, end up being NBL squared R delta T. So now I'm going to multiply that by B, that's B squared. Multiply that by N, that's N squared. Multiply that by L, that's L cubed. So yes, I'm going to get N squared B squared L cubed over R delta T. So not only are they numerically the same, that's not a happenstance. That's actually exactly consistent with all the equations we use. Isn't that kind of neat? Remember what I told you, when we're doing science and we have 2 branches of science converging on the same answer, we're more confident about what we know about it. What we just showed was an electromagnetic way of doing it. And I shouldn't really put it equals here. I'll just make this an implies. We showed an electromagnetic way of doing it, but we also showed a mechanical way of calculating the force. And lo and behold, even though it was an average force, we got exactly the same. So that's pretty remarkable. Any questions on that? That's a seemingly complex problem, but as you can tell, if you just take it piecewise, and that's sort of why I wrote the questions in the order that I did. You know, what is the flux initially? What is the rate of change? So I'm asking leading questions like the Socratic method, so that you can actually see, oh, okay, so I could have just asked what is the average force, or I could have just asked how much energy is dissipated, and you'd have to go through all this. But by asking you A, B, C, D, I've sort of handheld you and pointed out to you what steps to go through. So any questions on any of that stuff? All right. And remember, these documents will be posted in Google Docs. I usually do it immediately after class. If not, it's maybe an hour and a half after class. So let's look at another example, and this is going to be a very generic example. I've sort of done this derivation before, but I want to do it just formally and purely in symbols, so I have a result that we can use. So this is going to be example 2. I don't know what happened to my word example there, but it was just terrible. There, example 2. Okay, what we're going to imagine here is a uniform magnetic field. And I'm going to take this one, let's take this one to be into the plane. So we're looking at the little feathers at the back of the arrow. So it's a uniform magnetic field, and the strength of this magnetic field is just B. So again, I've listed it, that means we know it. Okay, so we know that. And what I have in here is this trombone bar, say. I think you go out in and out in and out while you're playing a trombone or whatever. Okay, so you have that. And what is this distance right here is going to be L. And then this distance to this little rod that's going to be laying across it is going to be X. Okay, but this thing's actually free to move. And in fact, it's going to move at a velocity V. Okay. So what I'd like to calculate really is the magnitude of the induced EMF. So E is equal to negative N d phi B over dt. But in this case, N is 1, and I'm just wanting the magnitude, so I'm going to ignore the negative. So I'm going to say E is just going to be equal to d phi B over dt, forgetting about the negative, just because, remember, I sort of hinted to you that the negative was all about Lenz's law, and it basically makes conservation of energy happen. And that's sort of why we learned that the induced current will act in such a way that it resists the change in flux. Okay, now what is the flux here? Well, the flux, remember, the magnetic flux is equal to the integral of B dot dA. Again, we have a uniform magnetic field. The area, however, is L times X. So we'll have B times L times X. So when we plug that in, we get d by dt of B times L times X. But the B and the L are constants. So we get B times L times dx over dt. Does anybody know what dx over dt is? It really is that simple. Don't be scared. You can say it or type it. Anyway, look, Clarence done turned his head. He's like, I'm not looking. Like when you see your friend that owes you money. Oh, I don't see him.
It's just 1, isn't it?
dx dt, not
Yeah.
1. Remember, it's this dimension right here, the distance from here.
Oh, right, right.
Okay. So anybody want to take a guess what dx dt is? How about unit wise? What would its units be?
Meters?
Yeah,
Yep,
We win.
meters per what? Meters per what?
Per second.
Okay, so the dx dt is,
Oh, wait, velocity.
there you
Right.
go, VLV. So that is a result that we can use over and over again. Anytime you have basically a moving thing through a magnetic field, especially when it's literally perpendicular to the moving metal, you're going to get an electromotive force induced. Now, you might recall,
I had to get up to get a tissue. So at first I was confused on what part of the problem we were in.
Gotcha. No problem. So it turns out this can be used all over the place. Like if you imagine an aircraft flying, the magnetic field of the Earth is there, right? We have a magnetic field around the Earth. It's like 5 times 10 to the negative 5th Tesla. So when you have such a magnetic field and you've got an aircraft that has highly explosive gasoline in it, you need to know all the random voltages you got running around the craft for, reasons of safety. In flight 880, in fact, it was a spare spark that ignited a tank, as best we can tell, ignited one of the fuel tanks and caused it to explode out over the ocean. That is a very real scenario. So what we might want to do with example 3 is say an airplane is traveling at 290 meters per second. Notice that's a little bit under the speed of sound. We're not doing the Concorde. Okay, meters per second in a region where the Earth's magnetic field is nearly vertical. I'll just say is vertical. That way we can say it's an exactly right answer. Okay. If its wingspan is 85.0 meters, how much voltage is induced? So remember, that's the word we're using here, induced. So there's this airplane. Basically, it looks, the aircraft from tip of the wing to tip of the wing looks just like this. It's got the fuselage, of course, in the middle, and it's flying through the air. We don't really care about which direction, what the polarity is. Is it the north wing or the south wing that's positive? It doesn't matter. All we care about is what's the total voltage that could come from this. And obviously, having a large wingspan, large L, and a large velocity makes it more likely to be larger. So again, we ignored the negative to get this result. We're doing the same thing here. So E is equal to BLV. Well, as I mentioned to you, the magnetic field is about 5 times 10 to the negative 5th Tesla for the Earth. The L in this case is going to be 85.0 meters. And then the velocity is going to be 290 meters per second. And I'm assuming all of these are 3 sig figs. If you multiply these out, I think you get 1.23 volts. So thank goodness for that very small magnetic field of the Earth. If it was bigger, we might actually have a problem. But 1.23 volts, that's not that bad unless you got a super low resistance metal that you're using, which could be from small cross section. Or excuse me, a large cross section or short length. It's surely not a short length though, so we can't deal with that. Not only that, it's going to have a lot of areas that are connected through rivets and all this stuff like that. So yeah, we don't have to worry too much about the stray voltage on an aircraft due to the magnetic field. Okay.
It does sound like something that the electrical, that the people wiring electrical systems for aircraft might need to take into account though.
Yeah, they might. I mean, and I'd like to. I wish I'd talked to some of my framers. I got some friends that are airframers in the Navy, or were and retired and stuff like that. So they did a lot of this work on the aircraft, both mechanical, electrical, all that sort of stuff. I would be curious to find out if anybody knows anybody like that. Do they take that into account? I do know one thing. I had a lecturer when I was in undergraduate. A guy from, I want to say he was from. No, I can't remember now. Anyways, he was from one of the large companies, Boeing. That's what it was. He was from Boeing, and he told me that they actually do design their aircraft to take on lightning strikes. They expect hundreds of lightning strikes and nothing to ever happen to it. So that's kind of interesting. But yeah, I would imagine that lightning strike is a lot more deadly than this 1.23 volts. Anyways, anybody have any questions on that? Okay, well, this actual application, you'll see your book has many other applications to it, but you can actually apply this to a lot of things. My daughter's got COVID right now, my youngest daughter, and it's been about 5 days, and she's 17 and healthy and all that good stuff, but she was having difficulty. She's just really exhausted, So I wanted to, find out what her blood oxygen saturation is. I happen to have such a device because I'm a career hypochondriac. So, so I took my pulse oximeter to her, and she was able to check her blood. But that pulse oximeter does, one way that can work is by creating a magnetic field across your blood vessels. And then creating that magnetic field, it can detect what kind of voltage difference is picked up, knowing the diameter, say, of the vessel. And then from that can tell the velocity of your blood. So those types of devices exist. Pulse oximeters can do that. Various other devices use, in this case, they'll use a lot bigger magnetic field, obviously. They're usually on the order of 5/100ths of a Tesla or something like that. But all you need is a battery to create a magnetic field. Remember, you used to make them when you were a kid by just wrapping wire around a nail. So that's really all you do. Now, the case of the MRI, that's really a super cooled, super powerful magnetic field, and it changes rapidly in time. And that actually causes the dipole moments of various molecules to flip back and forth. And when they do that, they give off little photons of light. So in addition to the cool pictures you get from an MRI, you also get this graph that's got little spikes on it. And each of those spikes corresponds to a certain energy, and you can look up those energies, and they tell you certain elements. That's, in fact, when my grandmother was diagnosed with Alzheimer's, we learned that was one of the things what was shown in the brains of Alzheimer patients was they had an aluminum spike. So that meant there was more aluminum in their brain than normally is the case. And for a brief period in the late 80s, people were saying, get rid of your aluminum cookware, stop drinking out of aluminum cans. I think the ultimate verdict on that was post hoc ergo propter hoc is not good logic. And in fact, it turned out to be the same thing that causes the Alzheimer's causes the aluminum buildup. So that was not a cause. All right. So any more questions on anything? Like I said, I'd just like to give you a little bit of background on some stuff where this is applicable. I went to East Carolina for my undergraduate and did a master's there, and they had a big medical physics program. So I can, sometimes give you some information on cancer treatments and various other medical things. Plus my wife's in the medical field. Let's give you example 4 now. What time is it? Or 11:41, plenty of time. So example 4. So in this case, we're going to consider that same setup right here, this little bar in this situation. And what I would like to know is what force is required to pull the rod. So I should have wrote that lowercase anyways. Example 2 above. What force is required to pull the rod? So that's a pretty straightforward question, but it's not quite as easy as you might think. What you got to realize is there's always, due to a magnetic field, there's always some kind of force on a current carrying wire, and that's given by that DF is equal to IDL cross B, which we've worked with. We've used to calculate the force on a semicircular loop of wire, all sorts of stuff like that. In this case, we're super lucky because the cross product just becomes regular multiplication when the DL and B are in fact perpendicular. And you can see this is clearly perpendicular to the B field, which is actually pointing into the page. So we could just say, all right, well, this means the force that the magnetic field is actually putting on the bar. If you assume the current, notice this this thing is going this way. So flux is what? Increasing or decreasing? When the rod is moving this way, is flux increasing or decreasing?
Is it it's increasing, isn't it?
It's increasing because the area is getting larger, right? So the flux is increasing, and according to Lenz's law, a current will be set up to oppose that change. So since the flux is increasing, it's going to try to fight that flux. It's actually fighting the change in flux, but it's doing so by trying to cancel out the magnetic field. So the magnetic field that exists is actually going into the board or into the page, and it's going to try to establish a current that comes out of the page to lessen that flux. So when you do use your right-hand rule to create a magnetic field coming out of the page, you see that this current would go around in a counterclockwise fashion. Do y'all agree with that? Can anybody not reach that conclusion on their own? Okay, so we know the current is going this way, and therefore I and DL points that way. And then, of course, when you cross that with B is pointing into the page. That means the force due to that magnetic field is pushing the rod this way. So you are actually have to at least bring that much force to the table to pull it along. So what we're calculating is what that force is. Well, that force is I times L times B. So we got I times L times B. That's our actual force. Now, what we do know is that the electromotive force, which is going to allow us to determine a current, the EMF is equal to B times L times V. And of course, we also know that E is equal to I times R. So if we know the total resistance all the way around here, we can say that I is equal to that EMF over R. So putting all this stuff together, I'm going to say I is equal to E over R, and E is equal to BLV. So we got BLV over R. Now I plug that into F equals Bill. So F is going to be equal to.
Oh, we can't see.
Oh, sorry. Thank you for catching that. I can tell when my students don't. I noticed this last night. It was a late class running like 7 o'clock at night, and I completely wrote out the screen. And I looked up, and I'd been out of the screen for like 3 lines, and nobody had said anything. Like they were, so I knew they weren't paying attention, and that's terrible because I wasn't paying attention either. So, anyways, so I have a B times a L already, and then I'm going to multiply this by the I, which is BLV over R. So you see that the force is going to be B squared L squared V over R. B squared L squared V over R. Of course, if you want to know more, you can say, okay, well, the force is B squared L squared V over R. That's a quantity that we want to keep and be able to use later. But you can also ask other questions like how much power is being dissipated? Well, remember, P is equal to I squared R. So we can actually calculate the dissipated power as I squared R. And we get, of course, I, which was BLV over R right here, which was here. So I get BLV over R. That's going to be squared times R. That would be B squared L squared V squared over R squared times R, which just gives us B squared L squared V squared over R. So that's the power dissipated. But if you also wanted to compare it to mechanical power, remember that work equals the integral of F dot DL, or we can call it DX if we wanted to. Then power is dW dt. And you can sort of say, well, that's equal to the integral of F dot DL over dt, which gives you power is equal to force times velocity. Well, if we take that force that we calculated, F equals B squared L squared V over R, and now multiply that by the velocity, we get B squared L squared V squared over R, which is exactly the same as the force dissipated. So that original assumption that I made about the power is exactly right. Any questions on that? I don't know why I put that there. That was bad. This was supposed to be the P. I went to write P equals F times V, and I wrote F and then started writing P. Sorry about that. So we can see in this scenario, we got power two different ways, and both of them gave us exactly the same results. Again, just like the problem we worked a second ago. Any questions on that? Just got another student coming in. I don't know if they were bumped out or what. No, any questions on this whatsoever? Everybody follow that argument and everything? All right. Well, we have a generalized form of Faraday's law. And we also have the transformer equation that we got to cover. I'm going to go ahead and do the transformer equation, and then I think I'll have enough time to even do the generalized form of Faraday's law. So let's start with a simple idea. So this is just a discussion more so than an example. So if you take one of your Pilgrim belt buckles, I've hinted at this several times. So remember the belt buckle that everybody wore to play for Thanksgiving or whatever, look like this. Now just imagine that as iron. And in fact, if you ever look at one, they're usually iron. They got a bunch of little plates, all sort of like, looks like it's welded together or something, or glued together or something, but there's just a bunch of metal plates. And that's actually to make it more efficient. It stops eddy currents that can steal some of the power. And sometimes, at least the older ones, they used to stick it in a carcinogenic oil, which I was fortunate enough to have spill all over me one time, because we had a device that could bump amperage up to quite a high amperage, quite a low voltage, but a big transformer is necessary for that. But all of that stuff is, basically the private sector and researchers figuring out ways to make this as efficient as possible. And to make it as efficient as possible, they found that you make this out of iron. And then what you can do is you can take the wire coming from some source and wrap it around like this. And let's say this voltage here, from here to here, is the primary voltage. And the number of turns over here is NP, the primary number of turns. Now, what's going to happen, you guys recognize this, if there's a current running this way, then you grab that with your right hand with your thumb pointing in the direction of current, and that tells you the magnetic field is wrapping around this. If we were looking that way, it would go counterclockwise. Well, that means in the center, there's a magnetic field that goes up. Well, this iron sort of corrals that magnetic flux and causes it to go all the way around, around, and around. And the more efficiently you can maintain that flux in there, the more efficient the transformer is. And transformer technology is pretty good. We're in the 90% to upper 90%. Now, if that magnetic field, which is changing because it's an AC current, if that magnetic field is truly 100% staying in there, then the flux you have on this side is the flux you have on this side. So then you can take and wrap a bunch of turns here, and I'll call that NS for secondary, and out is going to pop a voltage V secondary. Well, according to Faraday's law, we know that VP, ignoring the sign right now because it'd cancel out anyways, the V primary would be N primary times D phi B over DT. And we know that V secondary would equal N secondary times D phi B over DT. Now, this would be on the primary side. This would be on the secondary side. But if we're really, really, really efficient, and like I said, our technology is pretty good on transformers. If our transformer is really efficient, then this flux right here will be equal to this flux right here. Because of that, you get the famous transformer equation, more than meets the eye. No, different transformers than that one. Robots in disguise. So there's a VS over NS, and it's normally stated something like this. The secondary voltage is equal to NS over NP times the primary voltage. Okay. Now what that means is, notice if the secondary voltage or the number of turns on the secondary is bigger than the number of turns on the primary, then this number is bigger than 1. And it's a step-up transformer. So that's a step-up transformer. So they use this, for instance, in coming from a power plant, which actually might not produce that high a voltage necessarily. But what they've discovered is when you run those lines over large country fields, that's a lot of power wasted. And remember that power, P, is equal to I squared R. Well, it turns out the number of amps that go out is sort of what your power station is proud of. So if you have a power station or somewhere like a hydroelectric facility or something like that, they're going to produce a certain amount of current. And that's really what they've got to produce, because if you're going to serve, say, 400 houses, every house requires 200 amp service. That's the regular service that most houses get. So 200 amps times 400, you're set to a certain number of current, a certain amount of current going out of that plant if you built that plant for that particular neighborhood, right? So if you just send out that much current at whatever voltage is developed at the hydroelectric plant or whatever power plant you're using, then I squared R is going to be a lot of waste because that I is so huge. Well, it turns out when you use a step-up transformer, the factor that the transformer steps the voltage up by, so let's say it went from 10,000 volts to 1 million volts. So that's a factor of 100. So NS over NP would equal 100. Well, what you've just done is you made the voltage go from 10,000 to 1 million. And that's the high voltages that you see on those towers going through country fields. But there's a similar equation to this with these two reverse, and that being I secondary and I primary. So we have another equation, I secondary is equal to N primary over N secondary times I primary. So by cranking the voltage up by a factor of 100, you've cranked the current down by a factor of 100. So instead of 400 times 200, which would be 80,000 amps, you now have 800 amps. Okay. So you went by a factor of 100, 100 squared is 10,000. So you saved 10,000 of the power that you would have lost just by doing a step-up transformer from 10,000 volts to 1 million volts, assuming again that it would be carrying 80,000 amps. Okay, so that's how this is used. Let me give you an example. So we talked before about full wave rectifiers and stuff like that. So when you plug in your cell phone, say, to one of those plugs that plug right into the wall, well, that thing has a lot of stuff going on there. For starters, most of the things that you have in your house run on DC. So most of the stuff like, you know, microwaves, well, actually microwaves not a good example, toasters and ovens and things like that, they run on DC, and your computer runs on DC. And whenever that happens, that means you've got to take power from your wall, which is an AC signal, meaning the current alternates every 60th of, basically every 60th of a second, one whole cycle goes. So you go from 0 to the peak voltage, which is square root of 2 times 125 roughly, to 0 again, to peak voltage in the opposite direction or the opposite polarity, to 0 again. That happens every 60th of a second. And what we have to do is turn that into a constant voltage instead of one that wiggles in time and even reverses in time. And to do that, we use a wave rectifier, which is basically a system of diodes. If you put one diode in there, then you can cut out the negative part of the voltage, that little loop down there, you can cut that out. But if you put two of them in there, then you can steal the positive part from the regular diode, and then flipping the other diode will allow you to take the negative part and flip that to a positive. So instead of getting a sine wave, you get just a bunch of the vertical humps right next to each other. It's literally like taking the downward hump and turning it upside down. Now, if you string that along with a resistor and a capacitor, that slows down the process of voltage changing. So that voltage will come up for that one hump and then slightly dip down and then run into another hump. So ultimately what you're getting from a full wave rectifier is, and this is true for current as well as voltage. I just happen to be talking about voltage. So we can say voltage and time. Initially, we had something like this. Okay. So when we put in a full wave rectifier, if we do a half wave, we get just this part. And we're actually going to lose a little bit of voltage. In fact, it's like the turn on voltage for the diodes, like 0.5 volts or something like that. So instead of 125 root mean square, you're going to get like 125 minus 0.5. Okay. But if it was a half wave rectifier, this would just be flat. And then you'd have another wave like this right here. And then this would be flat as well. But if you use a full wave rectifier, then this one's going to turn over and be slightly shortened like the other one. So that's a full wave rectifier. Now, with that gadget, which we'll call a full wave rectifier, now if you take that and connect it to a capacitance and a resistance to ground like that, that's going to slow the process of voltage changing. And in so doing, instead of getting this green one, you're going to get this blue one, which will fall down like this and then come up and fall down like this and come up and fall down like this. And that's about as close as you could hope to get if you make the optimize the size of the capacitance and so on and so forth. Ideally, you would like to have DC look just like that, but instead you're going to get with a little 120 hertz ripple. Okay. Now that 120 hertz ripple is going to come out at like 125 volts roughly, ignoring details of peak to peak versus root mean square. If you connect that to your phone, it will blow up. Okay, that's not a good thing. So the next step is you run it into a transformer, or the next step can be that you run it into a transformer like this. And if you had 120 volts and you wanted to turn it to, let's say, 5 volts, which is what your battery runs on. So I've got 120 volts and I want it to come out at 5.0 volts. That's got to be a step down transformer. And that's what you see on your telephone poles outside your house, because normally at your house through a neighborhood, if you have overhead wires, they're usually running at around 12,000 volts, something like that. And in some smaller neighborhoods, they get to where they're around, 1,000, and that's it. But either way, you got to step it down so it can come in as 240 for our house. And 240 is a little different. It's a triphasic thing, but never mind. So when I do this, I can use the transformer equation, which says that V secondary is N secondary over NP over VP. So what I would like to know is what's my ratio of NS over NP. So NS over NP should be equal to VS over VP, which VS is wanting to be 5.00 volts and VP is supposed to be 125 volts. So you can see 5 goes into 125 25 times. So NS over NP is 1 over 25. So in other words, I could have 100 turns on this side, and then I have to have only 5 turns on this one. That's not reasonable, but that still is what it would be. So there's N primary and there's N secondary. Oh, actually, that's not times 5. Sorry about that. That was supposed to be times 25. Yeah, it's times 4. It should be 4 there. Stupid arithmetic. So that's an example of using the the transformer equation. All you got to remember is this equation, which you can remember you're allowed an equation sheet. This is actually an equation that you're allowed to have on that equation sheet. So as long as you remember secondary and primary, that's what the S's and P's mean, and what the N's mean, you should be good to go. You can tell whether you need a voltage up or a voltage down. You can also use the equation that I told you about, which was equivalent, but it's IS is equal to NP over NS times IP. So remember the current, when you have a step up transformer for voltage, you have a step down transformer for current. So that's something to keep in mind. Believe it or not, this is more or less an example. Okay, so that was an example of charging in an iPhone. So I'll call that what, example 6? I can find that. Example 5. charging your phone. Okay, so now that we have that, I want to discuss Faraday's law in its more general form. So what we found in Faraday's law was that E the induced EMF, is equal to negative N d phi b over dt. Well, this right here can actually be made into something that looks a little bit different. But if you remember what Ampere's law was, I think you'll, in fact, like what it looks like. And what we're going to do is forget thinking about the number of terms right now. And I'm going to replace this with the integral of E dot dl. And that's equal to negative d phi b over dt. This is just a step away from making Faraday's law into a differential equation instead of an integral equation. But anyways, that's it. Now, remember we had before, Ampere's law was the closed integral of B dot dl is equal to mu 0 I enclosed. See how that looks like that? So if we find something with the symmetry of this and we apply it to E dot dl, we can actually find an electric field acting like a magnetic field because it looks like this side. And that's exactly what your book does with example. Let me find out what example it is. It's example 2914. So I will say, see example 29-14. In fact, let me share screen a second. This looks good. Okay, now we'll click over here. Hopefully I haven't lost it. So this is the example I'm talking about. So you have E produced by a changing magnetic field. So what you're imagining here is you look at, from the side, the south end of a big magnet, okay, is right next to the north end of a big magnet. If you want to look up how big these magnets can be, look at Los Alamos or any of the national laboratories. They'll have pictures of some of the big magnets they use. But anyways, you put them really close together like that, and you make a really uniform magnetic field, just like the ones we've been experiencing in class, or we've been drawing in class. So this is one where the magnetic field, remember, I told you magnetic field lines act like retired people in that they leave the north and go into the south. So the magnetic field lines are leaving the north pole and going up to the south pole. And of course, also remember that the Earth's north pole is actually a south pole of the magnet. So that comes in handy time to time. So we've got basically these field lines coming out of the page. Now, if all of a sudden you had the magnetic field change, maybe these magnetic fields were, or these magnets were actually created by wires wrapped around a big iron thingy. And then you slowly change the current going through it. That current going through those wires will cause the magnetic field to change. If you say that magnetic field strength change is dB over dt, then you can apply closed integral E dot dl is equal to d phi b over dt. And that's what's happening here. So in this problem, they want you to address this. A magnetic field B between the pole faces of electromagnet is nearly uniform at any instant over a circular radius of area radius R0, as shown in figure 29, 27A and B. The current in the windings in the electromagnet is increasing in time so that B changes in time at a constant rate dB dt at each point. Beyond the circular region, R greater than R0, we assume B equals 0 at all times. Determine the electric field E at any point P, a distance R from the center of the circular area due to changing B. So let me stop sharing now that we've had a discussion of that. And now I'll show you how we apply this. So what we have is a uniform magnetic field, which I'll just represent by maybe 4 or 5 little circles. something like this. So this is all supposed to be uniform. So the magnetic field's coming out, and it's supposed to be circular in shape, like this. So what we do is we draw a Faradayan loop. Remember, with Ampere's law, I called it an Amperian loop. So I'm going to draw, in fact, a Faradayan loop centered on the center beam of the magnetic field, okay, with a radius r, okay. Now, according to this, a current would be induced in this direction. So that's going to be our little DL, which I've told you guys before is basically R d theta in the theta hat direction. Remember, that's just in the direction of increasing angle theta. There's our theta hat right there. So that's our DL. So the left-hand side of Faraday's law, the closed integral of E dot DL becomes what we think, or excuse me, yeah, what we think is E, because of this, E should have a circular direction. So we're going to have a hypothesis that E is equal to some E of R pointing in the theta hat direction. So when I put that in here, I have integral E of R theta hat dotted with R d theta theta hat. Remember, the dot product is a linear operator, and we're doing it on a fixed R. So E of R and R are actually constant. So I'll get E of R times R out in front, and I'll get d theta times theta hat dot theta hat, which each of those are magnitude 1 because they got the hat on them and they're parallel. So the cosine of 0 is 1. So this whole thing's 1. And of course, we're going to go from theta equals 0 to 2 pi. So the left-hand side becomes E of R times 2 pi R. Does everybody follow that? It's just like what we did before with Ampere's law. Only the weird thing now is we're thinking of electric fields going in a circular direction. Remember, we didn't think that way before. We treated them as if they were diverging from a point, because we were dealing with point charges, right? But because of the symmetry between this equation and this equation, we know how this behaves, so this must behave exactly the same way. That's why we know the magnetic field or the electric field is going to go away around in this way. So that's our left-hand side. Our right-hand side, on the other hand, again, dropping the negative, is d phi b over dt, which is basically just the area, which is pi r squared times dB over dt. Okay, so this is for r less than big R, say. So for r less than the radius of the actual magnet, we get E of R times 2 pi R is equal to pi R squared times dB dt, which is really a vector quantity, okay? But we can now equate those two, and when we do so, you can see that we're going to get, oops, sorry. You can see that the R's are going to cancel out, and I'm going to get E is equal to R over 2 times dB over dt. So it does, in this case, vary directly with R. In other words, it's linear in R, just like we had before when we were dealing with charges for the electric field. Inside of the object, the actual electric field went up linearly, and then once you got outside, it fell off. So now I got to do the same thing for a Faradayan loop out here. So this is another R. And in this case, when we do that, just like there's a conceptual example like on the 3rd page of this chapter, and in that conceptual example, what you find out is that the flux only exists as B times the area of the magnetic field that actually exists. So in this case, just like before, I'm going to get E of R times 2 pi r for the left-hand side. And then for the right-hand side, I'm only going to get pi big R squared times dB dt. Oops, I wrote an R there, dB dt. So this part was for R less than big R. And of course, now you can see I'm going to get the normal scenario. I'll get E is equal to R squared over 2R dB dt. So it actually is inversely related to the radius, just like when we did Ampere's law, we got B is equal to mu 0 I over 2 pi R. See, the R dependence is 1 over R. That's the same thing we got here. The R dependence is just 1 over R. So if you actually made a graph of the electric field, it would be linear up until it got to big R, and then it would fall off like 1 over R from there on out, just like a current carrying wire. So that's a neat little problem. I really love it just because it's starting to let you see the similarity between electric and magnetic fields. Those are things that for a long time, no one thought were really that much related. And then when we discovered how much related they were, it made a lot more sense. And then when relativity comes along, relativity can in fact show that one person's magnetic field is in fact another reference frame's electric field. So anybody have any questions on that? Our time is up. You're free to stick around and ask me any questions. I'll wait for the last person to leave, but feel free to stick around and ask questions. Everybody's free to go.
Thank you, Professor. No question.
No problem. Thanks.
I just had a quick question about this upcoming lab. Is this the one coming up this week supposed to be the really big one? Or
No, it's I've got another week before I do that. I'm sorting that lab out myself still. So yeah, we'll probably be at least 2 weeks from now.
I'm just asking because actually I'll have to leave this lab a little earlier than usual, and I've already sent you an email with a letter explaining why. But yeah,
I got you. Yeah, I saw that. It's not a problem. Don't worry about it. I'll open up the lab early. It's called Optics 2, so you can start doing it a little early if you want, and that way you can finish it in the short time that you have.
Okay, thank you.
No problem. See you, Clarence. Krisha, Aiden.
I had a quick question.
Go for
I
it.
didn't want to, I'm not repeating what the other people said. I know they asked the same question twice about the homework.
Mhm.
The chapter 29 conceptual is due Wednesday, and then the other homework is due Monday. Just want to make sure that's correct. Okay,
Yeah.
just because typically it's the other way around. So I just want to make sure.
Yeah, I flipped this one just because I put the other ones back so far. So I flipped this one and they'll get back to the regular order the next time.
Okay, yeah, I just want to make sure.
No problem. Thanks,
Thank
Aiden.
you.
Nathan, William, anybody?
I sent you an email on Friday.
Yeah, I thought I replied to your email. I saw it.
I don't think I got a reply.
Okay. Well, actually, I'm looking for my phone now. Yeah, is it something private? You want me to kill the recording?
Yeah.
Okay, let me kill the recording for starters.